We have been discussing applications of differential form of the linear momentum balance, namely the Navier-Stokes equation, and we are discussing the applications hierarchically, going from the simplest to the complex applications. Okay. So, first we started with fluids at rest and rigid body motion, looked at the pressure distribution, and then we have discussed inviscid flows, in which we discussed the mainly the Bernoulli's equation. Okay. Now, we are going to discuss viscous flows. So, initially it was fluids at rest and rigid body motion, and there are no viscous stresses at all. Then we considered inviscid flows where the viscous stresses were negligible. Now, we are going to consider viscous flows, which means that there are viscous stresses. Okay. And we are going to discuss about flow between parallel plates, which I come across several times, and what is the main objective is to derive the velocity profile. Okay, so, let us look at the outline for this set of applications. Only of course, two words, as I told you, velocity distribution. The velocity distribution we are going to discuss for two geometries. The two geometries which I have come across several times earlier. What are they? Flow between two parallel plates, one in which the top plate is set in motion, other in which both plates are fixed, but pressure driven flow. For example, something pushes water through the between the two plates, let us say a pump which pushes the water between the two plates. And we have seen this velocity profile, even used them. We are going to finally, I would say, derive those expressions. Okay. We have been telling this towards end of fluid mechanics part, we will be deriving the expressions, and that is what we are up to now, derive this velocity profile and this velocity profile as well. Okay. In terms of terminology, so far I have been using words like configuration, geometry, example, etc. Now, time has come to use more formal words. Okay. They are called planar cuvette flow, the first one, and the second one is called the planar Poiseuille flow. Now, why is it planar cuvette flow, planar Poiseuille flow? Moment you say cuvette flow, it represents the flow between two concentric cylinders. We have come across this earlier. When we discussed about viscosity, an example of Newton's law of viscosity. When we discuss about viscometer as an example of application of Newton's law of viscosity. So, this is the cuvette flow. So, it is in cylindrical coordinates, because we are considering a similar flow in terms of Cartesian coordinates, it is called planar cuvette flow. Now, similarly, when you say Poiseuille flow, what represents Poiseuille flow is flow through a circular pipe, and because we are considering an analogous flow condition under Cartesian coordinate, it is called planar Poiseuille flow. Okay. So, cuvette flow and Poiseuille flow in general represents flow in cylindrical coordinates, and because we are considering analogous flows in Cartesian coordinates, and we are calling them as planar cuvette flow and planar Poiseuille flow. Okay. So, let us start with the Navier-Stokes equation. Now, we are going to consider the Navier-Stokes equation without any approximations. Okay. So far we have been making approximations, fluid at rest, rigid body motion, inviscid flow. So, we have been not considering the Navier-Stokes in entirety, we have neglected certain terms. Okay. Now, we are going to consider the full form of the Navier-Stokes equation, okay, and that is the Navier-Stokes equation. First we said the velocity is 0, fluids at rest, then we said the entire fluid body has one velocity, all the points have the same velocity. So, we can represent as one acceleration term on the left hand side. Then we neglected all the viscous terms on the right hand side. Okay. So, now we are considering all the terms. Okay. Now, the Navier-Stokes equation we have written only one in only one direction. Solving Navier-Stokes equation including all the terms is so difficult, really a formidable work, because we will have 3 direction equations, have continuity equation also. So, now what we are going to do is consider examples or cases, geometries, problems, etc., where we can get an exact analytical solution. So, we limit our scope, being introductory course, we consider only those cases where we can get a analytical solution. What do we mean by that? For example, let us say you can get V x as some function of y, okay, x velocity as a function of y. Other approach is numerical approach, where you get V x as different points of y, not as a expression, you get only in terms of numerical data, okay, numerical answer. Okay. So, we are going to consider only cases where exact analytical solution is possible. So, what should you do for that? Okay. Make assumptions, approximations not for an entire class of flow, but specific to the problem. This should be kept in mind. When we say approximation here, we made approximation for a class of flow. What do we mean by class of flow? Class of flow where fluid is at an rest condition, where the fluid moves as a rigid body, they are a class of flows. Similarly, a class of flows called unized flow. Now, all are viscous flows only, but these assumptions, approximations are problem specific. Given a particular problem, given a particular geometry, etc., for that particular example we will make approximation assumptions, that we will understand as we go along. Okay. So, though we take the entire Navier-Stokes equation, now the assumptions are not for a whole class, but specific to the problem. Okay. That is the difference between this approximation and this assumption or approximation. Okay. So, now let us take the planar cuvette flow, now that we have understood the terminology. Now, what follows should be very easy to us, we have discussed this several times. Flow between 2 parallel plates, okay. We have come across this several times, flow between 2 parallel plates, okay. And the bottom plate is stationary, okay. The bottom plate is stationary and the top plate moves at a constant velocity, okay, Vp. And okay, fluid motion is caused by fluid being dragged along by the moving boundary. Because this plate moves, that plate drags the fluid along with it and hence causes motion in the region between the 2 plates. Okay. What is a more formal way of saying this? That is little more informal. We say fluid is being dragged by the plate. More formal way of saying that is the flow establishes itself, okay, that is what happens due to the viscous stresses caused by the moving upper plate. That now becomes very clear. The previous statement is a little more informal, saying that moving plate drags the fluid along with it, hence sets the motion between the 2 plates. Really what happens? Because of the upper plate moving, there are viscous stresses, and because of that the flow gets established. Okay. Now, what are the flows which are similar to this? Okay. What are the flows which are, what is the flow that this geometry approximates? Okay. One is familiar to us, the other is almost similar to that. What is that is familiar to us? We have come across this viscometer arrangement when we discussed few classes back the application of Newton's law of viscosity. What is that we saw? We have a inner cylinder which is rotating, the outer cylinder is stationary, we have a fluid, let us say water or any viscous fluid between the 2 cylinders, and then we measure the torque and use that to calculate viscosity. Okay. We also said that this cylinder, this is the actual cuvette flow, is this, okay, which is a flow between 2 coaxial cylinders. Now, our geometry is flow between 2 parallel plates, one is moving, other is stationary. Here again the flow is between 2 cylinders and one is rotating, other is stationary. So, in that way they are analogous. When is it is valid? it is valid when we already discussed that this gap between the two cylinders is very small. When the gap is very small, then the flow in taking place, the flow between the two cylinders can be approximated to flow between two plates. Okay, that is the condition. Okay. Now, so that is in the field of instrumentation or measurement. What is the other example more of engineering application is the example shown here, which is a shaft bearing. What does a shaft bearing mean? You have a rotating shaft here, and then you have a housing which is similar to a stationary cylinder, and then here you have a lubricating oil. Of course, this is always or almost a high viscous oil, so that the friction is reduced between the rotating shaft and the housing. So, once again this configuration is also similar to our case, or our configuration approximates this configuration. Why is it? Because you have a rotating cylinder, something like our moving plate, and then you have a housing or stationary cylinder which is something similar to our stationary plate, and the gap usually, of course, that gap is usually not very large in a shaft bearing. There is a very small gap, and there is a high viscous oil there. In our case, a viscous fluid array, a fluid where our viscous stresses are going to be included, and that flow is between the two plates. Okay. So, what we are discussing is a Cartesian coordinate system, so that our complexity is reduced, and though this arrangement cannot be realized in lab, we can't have two plates like this. In a lab we can't have two plates like this, make it move and then make get a velocity field between them. But how do you realize is like these two cases, have a fluid between two cylinders and rotate one cylinder, you can get a similar velocity field. Okay. And if the gap is very small and both are this Cartesian configuration approximates the cylindrical geometry. Okay. That is the idea. Okay. So, in terms of nomenclature, now x coordinate, y coordinate, okay, and this is the our front view, and gravity acts along the y axis, okay, and this is a moving plate, the velocity of the plate is Vp, and this is a fixed plate, and fluid has properties rho and then viscosity mu. The distance between the two plates is h. Okay. Okay. So, now first we will have to start with the continuity equation. Okay. Let us start with the continuity equation. We will consider steady flow. What does it mean? Suppose you have these two plates, and let us say before you start the experiment, just imagine, suppose if you are able to realize this in the lab, and these two plates are stationary. Let us say time t equal to 0, you start moving the plate, there is some initial transience, we are not going to consider that. You set the plate in motion, and now the velocity field reaches a steady state condition, and that is where we are going to focus. So, we are going to consider a steady flow, and we are going to consider incompressible flow. In this case, it is incompressible fluid also if it is water. Okay. So, that is the continuity equation for incompressible flow, which is del dot V, the divergence of velocity vector, is equal to 0. In terms of the velocity gradients, it is dou Vx by dou x plus dou Vy by dou y plus dou Vz by dou z is equal to 0. Now, we will consider flow only in the x direction, As I told you some time back, we are not going to solve the complete Navier-Stokes and continuity equation. We are going to make assumptions specific to the problem. So, when I say specific to the problem, we are going to consider steady flow. Of course, incompressible flow comes along with the Navier-Stokes equation. Now, this is an assumption which you are going to make for this particular problem, flow only in the x direction. What does it mean? I have flow only in the x direction, and in the y direction there is no flow, and in the z direction there is no flow. Okay. No flow in the y or z direction. That is also intuitively understandable, because you are setting the plate to movement in this direction. So, you expect the flow only in this direction. We are not have, there is no driving force which can cause the flow in the y direction or the z direction. So, no flow in the y or z direction, V y equal to 0, V z equal to 0. Now, let us see what is the implication of this, that is what we conclude from the continuity equation. Let us substitute in the continuity equation. Okay. We have dou V x by dou x, V y is 0, we have got a 0 here, and V z is 0. So, this term is 0, which means that dou V x by dou x is equal to 0. What does it physically mean? Dou V x by dou x tells you change of V x with respect to x. Now, because that is 0, we conclude that V x does not vary in the flow direction. The flow direction in this case is the axial direction, that is what is shown here. V x can be a function of y, that is what is shown here. We are going to see that shortly. V x will linearly vary with y, we are not telling anything about that. What we are saying is whatever be the function V x of y, that does not change as you go along the flow direction. So, whatever profile you have here, the same profile here, the same profile here, that is what we say as fully developed flow. Okay. So, now what is the conclusion? We said V x not equal to 0, then we assumed that V y is equal to 0, V z equal to 0. If you do so and use a continuity equation, you conclude that the flow should be fully developed. You cannot have a condition where V y equal to 0, V z equal to 0 and V x varies with x, that cannot happen, that will violate the continuity equation, that is a conclusion. When V y 0, V z 0, V x cannot vary with x, V x can be a function of y, but along the flow direction V x cannot vary. If it varies, it is not correct because it will violate the continuity equation. Okay. Now, what we next do is, as part of our assumptions specific to the problem, I say that the plates are very wide, very wide in the z direction, which means that we are somewhere in between, and so there is no variation of x velocity in the z direction. Very wide plates, when I say wide, this is width, okay, this is width, a very wide plate, and so there is no variation in the z direction. V x does not vary in the z direction. So, if you take this, V x is this, V x does not vary in the z direction. So, we assume, once again it is an assumption, that dou V x by dou z is equal to 0. Okay. Dou V x by dou z is equal to 0. Okay. Now, what does it leave us with? Okay. Let me show that. What do we infer from all this? We said V x of course cannot vary in the x direction based on the continuity equation. Now, based on this assumption, we are saying that V x is assumed not to vary in the z direction. So, only direction in which V x can vary is the y direction. Okay. This V x not varying with x direction is a conclusion from the continuity equation. V x not varying with z direction is an assumption. So, V x will vary only in the y direction, which we call as the lateral direction. So, only this derivative will remain. What is that? Variation of V x in the y direction, that derivative will not be equal to 0. Okay. So, what this slide tells you is set of a combination of assumptions and conclusions from continuity equation. We have made lot of assumptions specific to the problem, and one conclusion or derived result, I would say, from the continuity equation. What are the assumptions? V y equal to 0, V z equal to 0, dou V x by dou z equal to 0. What is the conclusion from the continuity equation? Dou V x by dou x is equal to 0. Okay. So, let us list all of them in this slide. Dou by dou t is equal to 0, that is from the steady state assumption, and just like we discussed in the previous slide, V x is not equal to 0, V y equal to 0, V z equal to 0, we have assumed them. From the continuity equation, we proved that dou V x by dou x is equal to 0, and then we said dou V x by dou z equal to 0, let us assume that Vx does not vary in z direction, and which leaves us with the derivative a non-zero value for the derivative dou Vx by dou y. Okay. So, now let us put all these I would say assumptions and conclusions from continuity equation in simplifying the Navier-Stokes equation. So, first we start with continuity equation, state few assumptions, arrive conclusions from continuity equation, and then simplify the Navier-Stokes equation. Let us take the x component of Navier-Stokes equation, let us see what happens. Okay. Left hand side as usual we start with the Navier-Stokes equation written from the material particle point of view, and that is why we have left hand side rho dVx by dt written in expanded form here, okay, and right hand side we have all the forces. Now, it is steady state. So, dou Vx by dou t is equal to 0, and then we have deduced from the continuity equation that Vx cannot vary with x. So, this gradient is 0. Remember, Vx is not 0, the gradient here is 0. Next term we assumed Vy as 0. So, next term is also 0. Next term we assumed Vz is 0, of course, Vx is not a function of z. So, that term also vanishes. So, entire left hand side vanishes and becomes 0, and what does the left hand side represent? It represents the acceleration term. You have a temporal acceleration and a convective acceleration, both the terms vanishes. Okay. Now, putting it the other way, we made assumptions in such a way that the left hand side vanishes, that is the other way of looking at it. We have the assumption would have looked disconnected. Now, the reason for making those assumptions is that we made those assumptions so that the left hand side vanishes, both the temporal and convective action vanishes. Now, why should we do that? What would happen if the left hand side were to be present? Okay, let us discuss that. Suppose let us say we do not assume steady state, what will happen? You will have this dou Vx by dou t term on the left hand side. You will see shortly that we will result in a ordinary differential equation. That is also obvious, because the time variable is gone now. For the present case, only y is independent variable. So, we are going to get the ordinary differential equation. Suppose if we have not assumed steady state, then we would have the time derivative also, and we would have resulted in a unsteady state or transient problem, and we would have to solve a partial differential equation. We want to avoid that. Being keeping in mind of the scope of the course, we want to study cases where the result is the equation simplifies to a ordinary differential equation. That is why we assumed steady state. Now, second, what would happen if we had the convective acceleration terms on the left hand side? Now, if you look at those terms, we have, remember, the velocity components are all unknowns. So, we have product of two unknowns, either the variable as such or variable into derivative of the variable, which means that they are non-linear terms. Non-linear terms are usually much more difficult to solve. That is why we made a set of assumptions in such a way that the convective acceleration also drops. Okay. So, the set of assumptions are driven by one objective for this particular problem, to make it simple, that to drive both the temporal acceleration and the convective acceleration term to 0, so that we get a linear ordinary differential equation. Okay. That is the whole idea. Otherwise, the assumptions may look little ad hoc. You are making suddenly Vy 0, Vz 0, suddenly gradient in z direction 0, but all are keeping this objective in mind, so that to keep the problem simple. Okay. Of course, if you take other courses in higher semester, you may not make this assumption, you may solve the entire Navier-Stokes equation under transient condition with convective terms, etc. Okay. Okay. So, now the left hand side is 0 and right hand side we have all the forces. Okay. We will take up the right hand side now. We are not discuss the right hand side, how it gets simplified, we will take up that right now. Okay. We will take it now. Okay. Now, let us write down the assumptions required. So, V x not equal to 0, V y V z 0, dou V x by dou x equal to 0, dou V x by dou y not equal to 0, dou V x by dou z equal to 0, okay, that we already discussed. Now, in this case, as I told you, what drives the fluid motion is because of the plate. You do not have any pump or anything which is pushing the fluid between the two plates. Okay. So, the motion of the fluid is caused by the movement of the plate. So, pressure is constant along the x direction, pressure is constant along the x direction. Why is that? Because there is no applied pressure gradient which drives the flow. So, dou p by dou x is equal to 0. You will see in the next example, which is a Poiseuille flow, because both plates are stationary in the Poiseuille flow case. Right now we are in the Couette flow case. The Poiseuille flow case, both plates are stationary. So, you need some external device, a pumping mechanism to pump the fluid through the between the two plates, but now no such pump is required, we are not imposing. This plate itself causes motion. So, pressure is constant along x direction because no applied pressure gradient which drives the flow. So, dou p by dou x is equal to 0. Okay. This we already seen, flow establishes itself due to viscous stresses caused by the moving upper plate. Okay. So, now let us see what happens to the right hand side. Left hand side we already seen that it vanishes, it becomes 0. Right hand side we have rho g x and gravity acts along y direction. So, g x is 0, and now because there is no applied pressure gradient along x direction, dou p by dou x is equal to 0. Now, let us come to the viscous terms. Now, dou V x by dou x is equal to 0. So, second derivative is obviously 0. Now, we do have this term dou V x by dou y is not equal to 0. So, we do have the second derivative, and then what happens to this one? Anyway, the first derivative 0 here, dou V x by dou z is equal to 0. So, second derivative is 0. So, we are left out the very simple equation, and because y is the only variable, it becomes a ordinary differential equation. Okay. So, we just reduced I would say a formidable Navier-Stokes equation, a very complex Navier-Stokes equation, to a simple linear second order ordinary differential equation, thanks to the assumptions whatever you have made. But for that it would have been very difficult, but we simplify the problem making several assumptions, and so that we result in a ordinary differential equation. In this case it does not even look like a Navier-Stokes equation, but do remember we started with the Navier-Stokes equation and simplified to this particular equation. Now, let us look at the y component of Navier-Stokes equation. Okay. Let us write that the y component of Navier-Stokes equation, and let us simplify that. Now, left hand side very simple, V y is 0. So, all terms just vanish. Okay. Other way of saying is, of course, there is no V y itself. So, there is no question of derivative here. Moment you do not have V y, none of the derivative exists. So, just because V y is 0, left hand side vanishes, you will not discuss anything further at all. Okay. Now, right hand side we do have rho g y because gravity acts in the y direction, and then because of that there is a pressure gradient, and what happens to the viscous term? V y is 0. So, all of them vanish. So, what do the y component of Navier-Stokes equation simplifies to the equation which we discussed for fluids at rest. Okay. Just a hydrostatic balance, the hydrostatic stress and the gravity forces balance each other, same equation which we discussed for fluids at rest along the y direction. Why is that? Because there is no flow along y direction. So, it becomes same as what I discussed for fluids at rest. Okay, now let us take the z component of Navier-Stokes equation. Let us write down that assumptions are known. We have seen this a few times now, and let us see what happens to the z component. left hand side once again, because V is equal to 0, the left hand side vanishes. Right hand side, there is no gravity along z direction, so that goes to 0, and all the viscous terms become 0 because V is 0. So, this gives us the pressure gradient is 0 along the z direction. So, there is no variation of pressure in the z direction. So, there is no variation of pressure along the x direction also, because there is no imposed pressure gradient. So, pressure does not vary along x direction, z direction, and varies in the y direction because of gravity only. Okay. Now, let us summarize the simplified Navier-Stokes equation, really simplified, really simplified. Okay. In the x direction, we had d squared V x by dy squared is equal to 0. Okay. All other terms became 0, only this viscous term remained. And then in the y direction, same as the equation is same as what we have discussed for fluids at rest. It is a hydrostatic pressure distribution. Okay. And the z direction, there is no pressure gradient.